Okay, so can you see now the full screen?
Yes.
Okay, so good afternoon, everyone. My name is Sarah Ahmed. I'm assistant professor in electrical and computer engineering at the University of Texas at San Antonio. And the paper that I'm going to present today is Smart Ultra Low Power Weigh-in-Motion System. This work has been a collaboration between civil engineering and electrical engineering at UTSA. So we'll start with the outline of the presentation. So I'll first give you an objective and background of the work we're doing. Then I'll discuss the proposed concept and go from there to some laboratory setup and testing for the proposed energy harvesting system. From there, I'm going to explain the electromechanical modeling for the same energy harvesting system that we proposed. And then we're going to talk about the circuit design for the whole WIM system. And then finally, I'll discuss the algorithm for the traffic data processing and show the results for this. So the objective behind this work is to be able to develop an ultra-low power microcontroller unit-based WIM system that can detect the vehicle, get their gross weight, get the speed, axle count, and classify them into 13 different classes as defined by the Federal Highway Administration. So if you can see in this figure, we basically are proposing a metal box, and this metal box is going to have 4 sensors. Those sensors are using piezoelectric sensors, and I'll explain what are these. And they're put on the sides of the plate. And once the car passes through them, then they're going to generate energy. This energy is going to be used for 2 things. So to light up or basically power this microcontroller that's going to be used as a WIM system. And they're also going to be used for harvesting the energy. So also to do like data analysis. So I'm going to be explaining that in more details afterwards. So just as a background here, what's a piezoelectric effect? It's basically the ability of the materials to generate electrical charge by having a mechanical stress on it. The piezoelectric sensors has been used in the past, and as you can see here, I'm just showing 2 examples which are very different. The one on the left is more of a medical application where they use it for an orthopedic implant, but it's also on the right-hand side, they use it for cantilever here underneath the bridge, that by the traffic-induced vibrations on the bridge, it will generate energy, and this energy can be used for other applications. This is very beneficial for power sensors in remote and hard-to-reach areas. So from there, I'm going to just give a little bit background on different vehicle detection systems that are out there. So I highlighted 4 of them in this presentation. The first one is a camera system. This camera system is like put at the intersection, probably everybody knows it. So the problem with this one is it's a very high cost detection system. It needs high maintenance, especially if it's foggy or at night. And also it needs a separate power supply. Plus there's a lot of data that it's taken from it, but it needs resources for data storage and data analytics afterwards. Another example for the current vehicle detection systems is the inductive loop detector, and that's commonly known and commonly used. It has a high accuracy. However, the problem with this detection system is the installation cost, because you have to dig in the pavement and put them, and also the maintenance cost in case there's like a road construction or an expansion and so on. And if anything broke it, then it has to be like dig again and taken out and put again. So its maintenance cost is high. Another example is the loop, road loops. So those road tubes that you see here, those are like the tubes, and they are used for detecting the car. So once the car passes on it, it will give a signal that it passed. And as you can see, there's 2 of them put at a place, the location that's known. So the distance between them will help that we can figure out the speed of the car. So they are high accuracy in axle count and classification, but the problem with them is they cannot calculate your weight. And also they don't work really well if you have slow moving traffic, because if there's so many cars packed up bumper to bumper, then you cannot really tell the difference between which car and the next one. Another vehicle detection system also that's commonly used is the microwave radar. And in this one, they can detect the vehicles, but you actually cannot detect the axles. And if they are behind each other, then you can miss some of the vehicles. So what we are proposing in this is a WIM system that's going to cover some of those detection methods. And I just wanted to highlight here a portable WIM system, which is a weigh-in-motion system. This one is a big one and bulky one that costs about $10,000. And again, it uses battery, plus it has an optional solar panel that you see on top of it. So what we're trying to propose in here, something simpler than this one, and that costs less and also consumes less power. So the proposed concept here, again, as I mentioned, it will be like a small metal plate. This enclosure is gonna, can I just, okay. So this enclosure is gonna be flushed with the pavement, and it will actually, whenever the car passes on it, it will generate energy. So as you can see, it will generate an AC signal like you see on the side here. This AC signal is coming from those piezo materials. So the way we're doing it is we have PZT discs. Each one is about 6.8 millimeters by 25 millimeters, and we stack them in parallel, and we use them in the corner of the enclosure. These ones, once it passes the car on, it will generate this AC signal, which we can then rectify in order to use it as an output usable for a microcontroller turning on, or any WIM system that you want to use to turn on. I'm sorry. Okay, so here's the laboratory setup for this energy harvesting. So we used this PZT stack, we used one of them under a UTM machine, and we connected it to a variable resistor. This variable resistor we're gonna change in order to, which corresponds to the load. So you're changing your load, and we wanted to see how much energy we can generate out of this PZT stack. And you can actually, there's a voltage probe to measure the voltage, and this is the scope showing the results. So as you can see here, for testing the harvester, one of the stacks, on the left-hand side, we have the relation between our load resistance, which we are changing, and versus the amount of power. Basically, when you change the resistor, what happens is you get a voltage amplitude, a voltage difference, and this voltage you use in order to calculate this power using this equation, which is P is equal to V squared over R. So once you calculate the power, then we can plot this curve that you see on the side, and on here it shows the effect of increasing the force. The force means the heavier cars or heavier vehicles. So as you can see, the smallest one is the red one here at 1.1 kilonewton, and it increases up to reach 6 kilonewton on the top. And again, a truck would be about 44 kilonewton, so it will be higher. And once we increase the load, then you increase the power, and we're generating higher power. The curve on the left here shows that the harvested power increases by increasing the force. So what we're leaving, by increasing the force frequency. So on here, we're leaving the force to 1.1 kilonewton, but then we're increasing the frequency, which means it's faster cars. So it will increase the power that it generates it. However, there's one important thing that you don't really want to run at any point on this curve. You want to run at this maximum power point. So this maximum power point means that you have to match the impedance of your system, which is RL, to the impedance of the piezo system. If you match those two impedances, then you can get this point, and that's the job of our electric circuit here, to generate this higher power at that point. The next step is we had one stack tested. Now we wanted to connect 4 stacks, because we said on the enclosure, we're gonna have one at each side of it. So if we connected those 4, we tested whether we should connect them in parallel or in series. So if you connect them in parallel, it means that you're getting similar voltage, but you're increasing the current, which means you're increasing your power. So that's the preferred option, because as you can see, you're getting higher power, and you also have a low matching impedance. So your external resistor that you need to put to match the impedance of the piezo will be a lower value, as you see from the curve up. So with that, we had some experimental results, but then we wanted to get an electromechanical model, or a model that can represent the system, and you can actually use it for predicting different values without really going to the UTM and testing. So in here, we're showing that this is the mechanical system. You have a certain mass that you're pushing a force on, and you want to have an equivalent of this in an electrical system. This is doable by defining this phi, which is an electromechanical coupling factor that would depend on the geometry of your piezoelectric materials and its properties. And we are generating this mechanical force. So this mechanical force in electrical system will be equal to voltage, while the velocity, which is the derivative of your displacement, or how much you're moving this thing, is basically analogous to the current in electrical system. So using this analogy, we are able to represent an electrical equivalent system, as you can see on the right-hand side in here. And on this one, you have the resistor And this resistor is analogous to your damping of your system. The mass is represented as an inductance, and your capacitance here is basically the inverse of the stiffness. So we have a paper published already on how to get the model, which you can refer to, and it's referenced in the end of the slide, on the bottom of the slide. And by doing this, you can have now an equivalent model of this PZT. This equivalent model will represent a voltage source. This voltage source is basically phi times F, which is the force, or it's the load that's coming from the vehicle. And then the electrical components, the inductance, the resistors, and capacitance, and then your load. What we need to know is we need to know what is the output voltage that we are generating from the PZT. This is why we're doing all this modeling. So this output voltage here, it can be found with using just a voltage divider between the voltage of the input, which is phi f of n, multiplied by the impedance ratio. And the impedance ratio in here is the parallel combination of this load and the CP. So this is the Z bar. And that's divided by the total impedance, which is the 4 of them in series. And here the equation shows that. With doing this electromechanical model, we can now represent this graph, which shows, again, the resistor effect with the voltage on the y-axis. And we can see that we are matching with the experimental results that we're having. So now this model is good to predict our results, and we can use it in order to predict higher loads as well. So in this example, we're showing 1.1 kilonewton at a different frequencies, 20 hertz and 62 hertz. And we're also running it at 4 kilonewton at different frequencies, 10 hertz, 40 hertz, and 6 kilonewton at 20 hertz. So it can show that for the whole range of frequency and force, you're able to predict pretty nice. So with this, we now have our PZT sensor ready, which is our energy harvesting. And now we want to utilize that in a WIM system. So this is the circuit for the WIM system that we're proposing in here, and it has 2 components. The first one is an energy harvesting circuit. And in this energy harvesting circuit, as we said, we are gonna have output of an AC signal that comes from the piezo. It's a high voltage amplitude, and I want to step down this voltage so that it can be reasonable to the input of a microcontroller that have a low voltage input of about 3.3 for this case. So we're gonna use a step down converter, which is a flyback DC-DC converter in this case. And in addition to that, like if the piezo is generating enough energy to turn on the MCU, then we're good. If it's not, then I'm gonna have a small battery in here that can feed also the microcontroller and make it run in case it's not. If the piezoelectric material here is generating higher power than what is needed by the MCU, then what happens is it's gonna feed into the battery and charge the battery as well. The other part of this circuit is what we call data processing circuit, and this is actually how can we use the signal in order to predict all this axle load and axle count, etc. So what happens in here is when a car passes over the enclosure that we showed in the previous slides, the MCU is gonna wake up. And once it wakes up, it actually takes about 15 microseconds to wake up, which is very short in comparison with a tire moving at about 60 miles per hour and passing the thickness of or the width of our enclosure. So we are sure that we're able to turn it on without losing any information. So once it turns on the MCU, then the MCU is gonna get the data of the voltage in a digital form. That's why it says here signal from A to D. So it's an analog to digital converter. And the signals are gonna be processed inside in order to correspond to our different things that we want to calculate. And that will be shown next as well. So here is an example of a class 9 semi-trailer truck. So we have the 5 axles. And once the tire passes through this enclosure, it's gonna generate the signal. So this signal, after we rectify it and we do the voltage divider to decrease it, sorry, I think, okay. Then it will actually rectify the signal in here as you can see on the bottom figure. Okay, so with that, we now can explain the algorithm. So once the data is going to go into the microcontroller, it will be digitalized. So this is digitalizing the output voltage that's coming from the piezoelectric sensor. And we are using a sampling frequency of 1.2 kilohertz. So, and this is restricted based on the MCU that we are using because it has a memory of about 4 kilobytes. However, this is current efforts to use another microcontroller that will have a higher power consumption, but it can also have a bigger memory so we can save the thing. Once it's digitalized, it is going to be rectified, and this is the signal that you're going to be using in order to do your algorithm. So in here, as you can say, our digitalized signals are smoothed using a moving average filter to remove the noise from it. So our raw signal is the blue curve. This is comparing a moving average filter of Windows side 3 and 5. So you can have a smoother waveform. The penalty of this is we have a little bit of a lower amplitude, but we need to do this in order to remove the noise, and we can then proceed by determining what is the peak voltage and what is the duration of the pulse. This duration of the pulse will help us for calculating the load frequency and the vehicle speed and the axle spacing, while the voltage amplitude will help us calculate our axle load, and that's actually applied in this classification algorithm. So with that, we actually went to the lab and did some lab testing. So we connected the piezo stack underneath it, and we connected it to the microcontroller. And I'll just run a small video here to show you how if it lets me. Okay, I'm sorry, it's not letting me run. Okay, so in here, as you can see, whenever the pulse comes up, it will actually show up the class. So we tested it for 3 classes: class 3, which is a pickup or a fan, and a class 9, which is a truck and a full trailer, and then the last one is class 6. And I'm sorry, if you can see it on the LED, it basically tells you the class that it classified and shows on here. So with that, I'll go to our conclusion. So we have developed an ultra-low power weigh-in motion system using piezo sensors, which can extract the speed, axle spacing, axle counts, and axle loads. The system accuracy is highly dependent on frequency measurement of the input signal, and that's why we believe that if we increase the sampling frequency, we can get even better frequency measurement. This is a current effort, as I mentioned before, for us to change the microcontroller to have a faster sampling frequency and a bigger memory. For the current consumption now, we're only consuming 3 milliamps in active mode. And in active mode, it basically means about 4 seconds, 2 seconds to read your piezo signal, and 1.5 seconds to do the algorithm as I explained it. And then after that, it turns to sleep mode, and then it turns on again once another voltage comes in. So we have done laboratory testing, which confirmed successful implementation of the algorithm. There is still a little more work to do, and we also would like to do field testing. So that's our future work on that. Finally, I would like to acknowledge this study has been funded by Tran-SET UTC and CPS Energy, which is San Antonio local utility company. And I'm ready now for taking questions. Thank you.
Thank you.
Hi, Sarah.
Yes.
Nice presentation. I have a couple of queries regarding the time that was assumed between each cars. So when you said the MCU would be able to switch on within like 15 microseconds and take the data, so it will hold good for a car following another one. And I see you also assumed a trailer where there are multiple axles, right?
Yes.
So what was the time gap that was assumed between consecutive axles, not the ones which are distant, but the consecutive axles? What was the time?
So we assume that between each, like if there's two different cars, this is going to be about 2 seconds. So, and it will, for any car to pass, even if it's going on a slower one, for something like this 5-axle, it will also take it about 2 seconds to pass. So that's why we stay reading for about 2 seconds, and then we do the processing for 1.5. In our current efforts, we want to do those parallel together so that we don't lose another car. So currently it's doing it consequently. So yes, if we capture one car, then we process it, then if another car passed at the same time, we're not gonna capture it. But this is what we're upgrading the MCU in so that it can do them with RTOS, which is real-time operating system, so it can do everything at the same time. It can actually capture, do the calculation and the savings. So if another car passes, you don't really use the data from that. Did that answer you?
Yeah, almost. So when you collected the data for the trailer, so you
Yes.
have shown the data for the consecutive axles, if you remember. So what was the time that was assumed in between? Was it sufficient for the MCU to capture that? Like, is it should be less than 15 microseconds?
Ah, okay, so you mean no, actually 15 microseconds is for it to turn on. And then it has to stay on for those 4 seconds, so it doesn't turn off. So, okay, now I got your question. So you mean like if there's a space between the axles, then it's gonna sleep, right?
Yes.
No, we're keeping it on for that time. So once it turns on, it stays for those 2 seconds for reading. So it will not turn off before that, and then it turns off.
Okay. Okay, thank you.
You're welcome.
Do you see the comment in the questions?
Yes.
I mean, in the chat box.
Yes. So is this applicable for both flexible and rigid pavements? I would say yes, although I'm not a really civil person. We have Dr. P, I think he's not on the call, but I would say yes.
Okay, we probably need to go ahead and move on.